Okay, so this video is going to continue the discussion of eigenfunctions of the Fourier transform using differentiation and multiplication symmetry. So let's start with functions that are Schwartz functions. And what do I mean by that? So this is going to be a Schwartz space. So these are going to be functions that are smooth, and they have the property that not only is f a rapidly decaying function, but all its derivatives are too. And what do I mean by rapidly decaying? What I mean is it decays faster than any polynomial. And what do I mean by that? Well, I'm basically assuming that the functions are they're really decaying really fast. And I just need some kind of assumption like that will tell me that if I take, like, I don't know, 15 derivatives or something. That's not how you write 15 derivatives. 15, if I take like the 15th derivative and I multiply by some like x to the 10 plus 1, some polynomial, I still want this function to be an L2. So basically, differentiate as many times as I want, multiply by any polynomials, and I still get an L2 function. That's basically the thing that I want. The condition I have here is basically that if I take some k derivatives and I'm going to multiply by any polynomial, then it's still converging to 0 as x is going to infinity and not to I. So that's the condition. This is the Schwartz function definition technically. But what I really want is basically all of these functions to be in L2. So this is just some stuff. If you're familiar with the topic, then it's interesting. It's a vector space. If you take a function in here, you take its Schwartz function, it's going to be in here. You multiply by a polynomial, it's still in here. If you differentiate, it's still in here. So this is some vector space of functions. And this is a subspace of L2. It's a dense subspace. So this is a fact, is that if you take x times f of x, then you get this derivative of the Fourier transform times this I over 2 pi. Now, let's go through this definition. I mean, through this fact, it's just standard. But if you do this x times f of x Fourier transform, well, that's this Fourier transform. Now, when you do, the trick is to identify the idea that if you differentiate this factor here with respect to k, and x comes down with negative 2 pi I. We already have an x down, so let's just think about this x is already being a part of this, and we'll think of this whole thing as a derivative of something. So if we have the derivative of this, we get negative 2 pi I, derivative with respect to k, that comes down. But since I have an x here, but no negative 2 pi I have to multiply by this this factor here, negative 1 over 2 pi I, in order to get rid of the negative 2 pi I that comes down. And so let me just factor out the negative 2 pi I. Well, if I move the I up, it becomes I over 2 pi. I have this derivative in here, and it turns out because this function is a Schwartz function here, f, you can then move the derivative out of the integral. That's here. And then this thing is just the Fourier transform of f. So it's I over 2 pi derivative of the Fourier transform. And that was what this identity was. So that's the proof of that. We're going to formulate this in terms of operators. So let's define xf to be the operator. Let's define x to be the operator that takes a function f of x and maps it to x f of x. So it's multiplied by x. Define df to be the operator that takes f, takes its derivative of it, and multiplies by I over 2 pi. Now, what's so nice about these operators? Well, in some sense, they represent the things that we were talking about earlier with Schwartz functions. Differentiating, multiplying by polynomials. This is multiplying by a degree 1 polynomial. This is differentiating. If you learn more about functional analysis with self-adjoint operators, unbounded self-adjoint operators, there's a lot of interesting things that you can learn about these operators. However, we're going to focus on these operators just living on the Schwartz space. So we're just thinking about them mapping some vector space S into itself, basically. Now, S is going to be made of functions, and same thing with D. They both map these spaces into itself. Also the Fourier transform, and we're going to be restricting to this space. We're not going to be thinking about general L2 functions or what happens with the domains, and there's all kinds of things that you can learn about adjoints and the domain of these functions, and it's very complicated and very interesting. However, we're just going to be focusing on Schwartz functions. And what we showed was that if you think about these operators as only on Schwartz functions, then if you take Fourier transform and then differentiate, that's this. By differentiate, I'm going to say differentiate, but I really just mean apply D. I might mix that up when I'm speaking. You do the Fourier transform and you differentiate. It's the same thing as just multiplying by x first and then Fourier transforming. That's the identity we just showed. What you can show is that the opposite identity holds. Where if you have Fourier transform differentiation is negative multiplied by x Fourier transform. And why is this useful? The reason is that when people do operator identities and such, it's often useful for calculations to be able to manipulate these operators in different ways. So for instance, if I have fx, maybe I want to do the Fourier transform first. I don't like doing x first. The idea is that if I want to move the x past the f, it turns into a d. So it moved over and then it turned into a d. Same thing here. If I have fd, if I do d first, d will move over here, but instead of becoming x, it becomes a negative x. Alternatively, if you have xf, the opposite of this, and I want to move it over the other way, then what I see here is that it's negative ft. So this, when x comes over, I get a Fourier transform. It turns into a d, but then I also get a negative sign. So anyway, so let's go over this identity. So there are two ways of getting it. I mean, I guess there's lots of ways, I guess, in general. The one way is like the standard way, is that you just calculate the Fourier transform of the derivative. So d is not quite just the derivative. However, let's just calculate the Fourier transform of the actual derivative. So you do derivative here inside the Fourier transform. Then what do you get here? So basically the idea is you do integration by parts because you want to calculate the Fourier transform of the function, not the derivative. So if you take the derivative away, then you get this thing, evaluate negative infinity to infinity, and then minus f of x, this thing where you put the derivative on here. Now, this function vanishes. So this is a Schwartz function. It vanishes very quickly at infinity. And negative infinity, this right here is just a phase that just oscillates. So this right here is going to vanish. It's going to be 0. So basically, when you have a Schwartz function, and this is some nice function, you can move the derivative over and you just get a negative sign. There's no boundary terms because we're integrating on R, suppressing the notation. So we have this. Now, when you do the derivative here, what happens? Well, you get a negative 2 pi I, and this is a derivative, with respect to x, so negative 2 pi I k times the phase, and then you get a negative sign here. So what happens is you pull this out, and you get 2 pi I k, and that just, you're left with the Fourier transform of f. So the Fourier transform of the derivative is 2 pi I k times the Fourier transform. Now, if you write this in terms of d, so we did the Fourier transform of the derivative, so let's do Fourier transform of d of f. That is I over 2 pi derivative. Now, f prime, when you do the Fourier transform, is going to be 2 pi I. So let's pull the I over 2 pi out. Fourier transform of the derivative of k. That's I over 2 pi times 2 pi I k. Fourier transform. So we see here the 2 pi's cancel. I times I is negative 1. So we get negative k f hat. Okay. Now, this right here is just x f hat of k. Because remember, x just says multiply by the x. So if you did f of x, that's just x f of x. However, the Fourier transform, we're thinking of the argument here as a k, so it's going to be k times that. So it's negative x Fourier transform of k. So it tells us that ft is negative xf. Ft is negative xf. So that was one approach. That's kind of like the standard approach. You just calculate it. However, there's this nice operator approach. Basically, the idea is that what we did was we calculated the Fourier transform xf, and you had df. That's what we had earlier. Now what we can show is if you do fd, you get minus fx. And it's just going to be a consequence of this identity and the identity that xn is negative nx, and that n is f squared, and then f cubed is the inverse of f. So using these identities, you could put them all together to get this right here. It's a consequence of just these identities. You don't have to do this integration by parts or anything like that. So let's just explore. It's a very interesting approach, and I personally like it. So we're going to show that nx is negative xn. So we're going to show what it is, and then we'll explain why it's kind of obvious. So let's do nx of f. So x of f multiplies f of x by x, and puts a negative sign on all the x's. So we get negative x, f of negative x. Now, we have f of negative x. Let's pull that negative sign out. Negative x, f of negative x. This thing right here is nf of x. This is multiplied by x, so it's going to be x nx, nf of x. That's this. And then there's that negative sign. So we get nx is negative x nx. That's this right here. And why is this obvious? The reason it's obvious is that x is it multiplies by x. N says take all of the x's over here and turn them into negative sign. However, on this side, the only thing that's different is that there is no x to multiply by a negative sign. So here, this x is going to get a negative sign. Here, the x gets its negative sign already. Basically, that's the idea. There's nothing really. If you just think about it, it's kind of trivial in a certain sense. However, it's nice to think about it that it's not that obvious. So this is what we call anti-commuting, which is that nx, if you want to change the order, you can change the order, but you get a negative sign. So let's calculate fd. Now, this is a common thing you do in group theory, which is that if you want to change the order of two operators, and one of them is invertible, you can just conjugate. So fd, you can write this as this right here, df with a conjugation on the outside. Now, why is this true? Well, kind of obvious if you just group these cancel, and you get fd, fd. However, this conjugation trick is actually really useful for this example. So we have df here, but we know the identity that we have up here, which is that df is fx. That's fx in here, and then we have this conjugation here. Now what we're going to do is combine these. N is f squared. So that's f squared x. F inverse is f cubed. Now we're going to use the fact that f squared is n. F cubed is f squared times f. F squared is n, so it's nf. So nf here. Now we know that this thing, I can move the n over, but I get a negative sign. So negative x n squared. N squared is the identity. Oh, that's the other identity. I need n squared is the identity, which is kind of equivalent to this. But n squared is the identity, because if you put a negative sign on if you do f of x, and you turn that into f of negative x, now if you put another negative sign in here, it'll just undo itself. So n squared is the identity. It undoes itself. So we have negative x n squared f. These cancel, and I get negative xf. So fd is negative xf. So what's the point of this? So the point is that so that we can do kind of simple calculations of Fourier transforms when multiplied by polynomials. So suppose we have a polynomial x, and we have p of x. What is p times the operator of x times p? So I mean, suppose we had x squared times f. Well, what is that? Well, that's you just multiply by x. You just do it. So this means apply x twice. That's what it means. Apply the operator x twice. X, x, f. Now, the first time I do it, I get x f of x. And I do it a second time, I get x squared f of x. So you can see that this operator x squared turned into multiplying by the polynomial x squared. And in general, if you multiply by a polynomial and the operator x, it's just the same thing as multiplying by a polynomial of the variable x. And now, if you do the Fourier transform of this kind of operator, Fourier transform of x squared, in general, what will happen, I mean, just what happens is that you have x squared. That's the same thing as fxx. Now, whenever you do the x, if you want to move it over, it turns into a d. So you get a dfx. You move the other one over, you get d squared fx. And in general, you see a polynomial quadratic x squared became the same polynomial, but it's with a d. So you see here of f, polynomial in x's and f, and every time you want to move one of these things over, well, this is just a number, it comes over. This x comes over, it turns into a d. This x comes over n times, you get d to the n. So you get the same polynomial, but instead of x's, you have d's, and it's on the left side. And oh, this should have a Fourier transform here. Or there should be an f written in here. Either way, there should be a Fourier transform. So you have f p of x turns into P of df. Basically, every time you have an x, it comes over and it turns into a d. Conversely, if you have a polynomial in d on the right-hand side, every time a d comes over, it turns into a negative x. So I get a P of negative x. So just like if I had Fourier transform of d squared, then it's Fourier dd. And so every time a d comes over, it turns into a negative x. A d comes over, and then I get another negative x. Or so there's no d anymore. I just moved it over. So now the d squared came over, and it become the same polynomial, but instead of having x squared, I have negative x squared. And if I had f d cubed, then I have negative x cubed in parentheses. So this is generally what happens. So these are some nice identities. So let's talk about this space here, Vn. We're going to call it Vn. And this is going to be all the polynomials of degree at most n. So polynomials degree at most n multiplied by our standard Gaussian, the e to the minus pi x squared. Now these are subspaces. So V0 is sitting in V1, is sitting in V2, et cetera, et cetera. We know that V0 is just all the constant multiples. Sometimes they'll write it as constant multiples, the complex numbers, times the Gaussian. And we know the Gaussian is is an eigenfunction of the Fourier transform. So what it means is that if you take Fourier transform of V0, that's going to be sitting in V0 because, you know, any multiple of the Gaussian, you take a Fourier transform, it's just going to be another multiple, the same multiple. And so it's this subspace, the one-dimensional subspace, is if you take a Fourier transform, it's still going to be lying inside the Fourier, the same subspace. In fact, they're equal. So as a fact, f of Vn is sitting in Vn in general, all these subspaces. So let's see why that's true. So before we do this is part of the proof, but before we do that, we'll do a simple calculation. If you have any polynomial at most n, what happens if you do dp, the polynomial, times the Gaussian? Well, well, I guess technically I need to write I over 2 pi. I kind of dropped that. But if you do the d, besides that d is just derivative. If you differentiate this, you get a polynomial derivative. It's a smaller degree polynomial. If you differentiate the Gaussian, you get minus 2 pi x times the same polynomial Gaussian. Now what happened here? This is just a constant. It doesn't change the fact what subspace you're in. This is going to be a degree n minus 1 polynomial at most. This is going to be a degree n plus 1 polynomial at most. So this is going to be belonging to Vn plus 1. So in general, I want to show this. So let's do f of some polynomial of degree n at most times the Gaussian. Now when I do this, this is Fourier transform p of operator x, the Gaussian. Now when I move the p of x over, it turns into p of d times the Gaussian. The Fourier transform, when I move it over, this turns into a d. The f hits the Gaussian, doesn't do anything because it's an eigenfunction with eigenvalue 1. So I get p of d times the Gaussian. Now, if I differentiate the Gaussian with this polynomial that's at most degree d, then what happens? Every time I differentiate it, I start getting down polynomials. So if I differentiate, well, I mean, I actually don't need to check it. I mean, I have it proved here. If you differentiate a degree n polynomial Gaussian, it increases it. Every single time you differentiate a polynomial times a Gaussian, it increases by 1. So if I have a Gaussian here, and I do lots of differentiation at most n times, and then adding them and stuff like that, then I'm going to get inside Vn. So in general, f of Vn belongs to Vn. So these are invariant subspaces for the Fourier transform. Now, in order for us to do some nice analysis, we would like to say that f is also unitary on this Vn. So this is a subspace. It's a finite dimensional subspace. And if f were a unitary operator on a finite dimensional subspace, it's basically just a unitary matrix on a finite dimensional subspace. And unitary matrices, there's a spectral theorem, which says that you can find an orthonormal basis on this subspace. The question is if f is unitary, just, the fact that it's unitary, and V is this invariant subspace, is that all you need to know in order to know that f restricted to it is unitary on that subspace? Or do you need some other information about f? And the answer is no. It is not enough to know just the fact that it's unitary and this is an invariant subspace. You need to know more. So I have just some conditions here that are enough. So for instance, if you know that Vn is invariant under f star as well, so not just f of Vn, but f star of Vn belongs to Vn, then that would also be, if you had this condition, that would be enough to know that f is unitary on it. The reason why that's true is we know that f star f is the identity, and f star is the identity. Now, if both of these f and f star, if you restrict to Vn and it stays inside Vn, then both of these identities will then still hold when you restrict to Vn, and so f restricted to Vn will have an inverse, which will be its adjoint. So if this is true, then f restricted to Vn is unitary. What about this condition? What about f restricted to Vn has range equal to Vn? Well, basically the idea is that because of this, because f of Vn is in Vn, it's an invariant subspace, and because of this in general, this right here tells me that it's an isometry. F is an isometry. This is from the Fourier inversion, basically. If f is, that tells you that f is an isometry, and this is an invariant subspace. So I have an isometry restricted to it. So the question is, when is an isometry unitary? Well, that's the case when its range is everything. So it's invertible. So this is another necessary and sufficient condition. 3, this is just sufficient, but it's not necessary. If Vn is finite dimensional, then that's enough. The reason is that 2, being an isometry and being unitary are exactly the same thing when you have a finite dimensional subspace. So it's just rank nullity. And so this is basically, this is the case for all of our examples that we have up here with these Vn's, because they're polynomials of degree n times a Gaussian, so it's degree n plus 1. So yeah, so I mean, this example, the question is, being unitary and this being an invariant subspace, is that enough to know this unitary? It's not enough in general. But for our specific example, the Fourier transform, it is true. So let's do an example to actually illustrate the fact that if you had just some general unitary operator, it isn't the case that if one of these fails, then you get that the fact that it's unitary anymore. It's possible that these things aren't true. So let's consider UF to be this shifting, so it's a translation operator. So basically it takes a function like this, and then it shifts it over by 1 to the right. Now U is unitary on L2, you can check that. So if you do this integral here, it's the same thing as f of x minus 1 squared dx. You just do a change of variables to shifting, and then you see these are the same. So it's a unitary on L2. It's also unitary because it has an inverse, which is U star, which is shifting the other direction. So it's on isometry and it's unitary. S plus, let's consider this subspace. This is going to be the subspace of all functions that are supported on the right-hand side. 0 on the left-hand side. Now, this subspace is an invariant subspace. The reason is that if I have a function like this that's supported on the right side, if I shift it over to the right, it's still supported on the right. It's just supported on the right starting at 1 or something. So 1, and this is supported here at 0. Now, the key thing about it is that because of the fact that there's somehow nothing here anymore, there's something wrong. This is still going to be an invariant subspace S plus, but it's not going to be, if I restrict U to it, it's not going to be unitary anymore. So let's see why. That first condition, which is that U star restricting to the subspace, it restricts in the invariant way. That doesn't hold anymore, because if you take this function here and you shift it to the left, then you see that it's no longer in the subspace anymore. So as an example, if you take the characteristic function from 0 to 1, and you shift it over, this is outside S plus. This is no longer in the subspace because it's not supported on the right-hand side. Another thing, so that's how 1 was violated. 2 being violated is that 2 says that the range is it has full range in there. So let's just see it. Has range equal to Vn, so it's a subspace. You restrict it to S plus. I just showed here that if I take any function over here and I shift it over, it's no longer having anything here. So if I had a function like this function is not in the range of my shifting function to the right when I'm restricting to the subspace here. So basically it's not going to be onto, it doesn't have full range. Another way of saying that is that the subspace of all the functions all the functions that are supported on this interval from 0 to 1, that belongs to S plus. However, the range of this operator is orthogonal to that. You could check that if you want. But it's basically these ideas that I just said. And 3, S plus is not finite dimensional. I mean, that's kind of clear. Because if you have all the functions that are supported on the right-hand side, then that's an infinite dimensional subspace. So you see that all 3 of those conditions failed. But for the Fourier transform, all 3 of them held. And we were fine. Why is that true? Well, I mean, the third one obviously true. Finite dimensional, Vn is finite dimensional. So that checks out. 1 holds because the fact is that we know that f of Vn belongs to Vn, but f star, its adjoint, is f cubed. So f being an invariant subspace, that means that f maps vectors in Vn into itself. So if I just apply it 3 times, it's also going to be in Vn, which is the same thing as saying adjoint belongs to Vn. So that means that 1 holds. And then 2 holding is just a consequence of that. It's like I said, f. It's what I said earlier about 2. So I'm not going to go into that. Okay. So what do we get from all this? We get an increasing sequence of reducing subspaces. So reducing is just saying that f Vn belongs to Vn. F star of Vn belongs to Vn. And based off these 2 facts, f restricted to Vn is unitary. And then these are finite dimensional, so we have a unitary matrix basically on this finite dimensional subspace. And we get this increasing sequence of subspaces that are growing. And in each of these, we could, for instance, we just have a Gaussian here. That's an eigenfunction. And then every time I'm increasing, I'm adding 1 dimension. And that's basically adding on a single eigenvector subspace. It's increasing the dimension of the eigenspaces of f. So basically, I'm just adding eigenfunctions every single time. So I can build a set of orthonormal set of eigenfunctions for the Fourier transform from these subspaces. The question is, will that then give me a basis for L2, where I'm going to be missing some functions in L2, basically, when I take the span, the closed span. The question is, how can we know it's complete in L2? I'm going to present a proof, which is a proof that I personally like. So let's see that proof. Suppose to know it's complete in L2, what you basically need to show that it's dense. That's all we wanted to show, right? The span of these things, dense. So let's take a dense subspace, the compactly supported smooth functions, or just compactly supported functions. And we want to show that any element of this dense subspace of L2 can be approximated by functions of some Vn times the Gaussian. Or sorry, Vn is polynomial times the Gaussian. So basically, we want to find some function g in some Vn, so that g minus f in L2 is less than epsilon. For all epsilon, there exists g, so that this is true. So, what are we going to do? What we're going to do is we're going to apply Stone-Weierstrass. So you got to be careful about Stone-Weierstrass because Stone-Weierstrass, if this, let's take V to be the union of all the Vn's. Stone-Weierstrass, what it would say is that if we had g minus f, the L infinity norm is going to be bounded by epsilon for some g and v. So because L infinity norm bound doesn't give you L2 bound, you need to do something a little tricky to, like a small trick in order to get an L2 bound. So you basically need to apply the L infinity bound to something else, not the function. That's why I chose compactly supported functions, because that's what I'm going to do. So let me first explain why it's okay to apply Stone-Weierstrass. Basically, let me just read this. I'll just read through it. By Stone-Weierstrass theorem, this is Lang real analysis, and I'll explain it in a second down here why it's okay. There exists a polynomial degree n, so that what am I applying? I'm applying Stone-Weierstrass to not f, but this function, and I'm not applying it to some function of v. I'm applying it to this. So what does that mean? So this is the function I'm applying to. F is compactly supported and smooth. So if I multiply by this Gaussian that has this growth at infinity, this is still going to be compactly supported function. And this right here is going to be my subspace here that I'm going to apply Stone-Weierstrass to. Polynomials times a Gaussian, but it's not the Gaussian, the one that I like. It's the Gaussian over 2, the pi over 2. Now this subspace here is self-adjoint, because if you just take adjoint, if you conjugate both sides, complex numbers, you got complex numbers, is nowhere 0, because if I want a function that's 0 somewhere, I can just pick a polynomial that's 0, but I could also pick a polynomial that's not 0 there, and separates points. So that's just a fact about polynomials. Polynomials separate points; they're nowhere 0, and the fact that they're multiplied by a Gaussian tells you that it's a subspace of here. So this is a subspace of C0R. And through these conditions here, Stone-Weierstrass will tell me that this subspace here is L infinity dense in this subspace here. So there's a polynomial p of x times my Gaussian pi over 2, so that it's nearby this function here. Now, why did I do it with this weird function? The reason is that this is the thing I actually care about. Some polynomial, it's going to be the same polynomial I have here, times the real Gaussian, the one I'm familiar with, the one I like, minus f. So now if I pull out a half a Gaussian, so basically minus pi x squared is minus pi over 2 x squared squared. So basically this Gaussian here is like the product of two Gaussians. So if I pull out one of these Gaussians, then I get this Gaussian and then half a Gaussian. And then in order to get an identity, I need the positive Gaussian and the negative Gaussian to cancel. This right here is the thing that I applied Stone-Weierstrass to. That's why I applied it to that. And this is the Gaussian. So this right here is going to be bounded in L infinity norm. So it's, or maybe I should say less than or equal to epsilon here times the Gaussian. So what does that tell me? That tells me that P, this right here, it's just this thing. I have the L2 norm squared, so I'm going to be squaring it and then integrating it. And then that's going to be bounded by this thing squared and integrated. That's this bounded by epsilon squared. And then when I squared this Gaussian here with the half, I just get the original Gaussian that I had earlier. And then the integral of this Gaussian is just 1, so I just get epsilon squared. So what I proved was that this thing squared is less than or equal to epsilon squared, which is exactly what I wanted, which is right here, basically. Or sorry, not that. The L2 norm one, which was somewhere. This one. Okay. So that's what I showed here. What it shows is that the polynomial times the Gaussian is dense in L2, because I took any compactly supported function that was continuous, and I should be approximated by this in the L2 norm. And because continuous compactly supported functions in L2 are dense, and that's all I need. So note there are other proofs. There's a slick proof using complex analysis on the Wikipedia page for Hermite polynomials. Basically involves taking some kind of function, f, that's in L2, and you assume that f is orthogonal to v, that subspace that I made. It's orthogonal to all the polynomials times Gaussian. Then what you do is you cook up some kind of function G that's entire. And you basically use it to show that F is 0. I don't remember exactly how the proof goes, but if you look it up, it's very interesting. It's one of those slick proofs that they use a lot, complex analysis, and it's good to be familiar with some of those ideas. I don't use it very much, so I don't remember off the top of my head, but you can go check that page. So let's continue. So from what we had was that we showed that V, this is dense in L2. And in each of the Vn's, this is the union of n Vn, I could find an eigenfunction decomposition for the Fourier transform. And as I'm increasing n, I'm just adding in more eigenfunctions. So I can construct an eigenbasis. However, we didn't actually write out what an eigenbasis was. So let's continue that in a little bit more. However, I'm going to start a new video and we'll continue the rest of this. So what we talked about was this polynomials and this space here. We showed that it was dense in L2. We talked about we would have some eigenfunction decomposition. However, I didn't say very much about what it does. So I'm going to go stop the video and then continue on the next video in the series.